Hello everybody, and welcome to today's session. So we're meeting after a long time. Uh, we had a sort of a gap, and I hope you guys are preparing well. There's not a lot of time left for the examination. So I have an interesting topic for you today in physics, which we'll pick up and try to understand the concepts briefly. And just like every other session, solve a few problems. So the thing is, initially, this is one of those topics which initially seems really difficult, but it's actually not because you just have to understand what's happening, right? The concept, because it's difficult to visualize when all of this happens in the first attempt. Such as that, so is the topic. It's called wave motion. So I'm sure you would have come across wave motion equations and stuff like that while preparing. So it becomes slightly challenging to understand what's happening really in the motion. But the fact is, once you understand this, there can't be difficult questions made in this section, right? There are topics like mechanics, rotational motion, and other topics which, even if you understand, you require so much practice to be able to ace the problems, because they might give you some problem from some other model which might actually blow your mind away, right? But wave motion and what do you say, modern physics and topics like these, vectors in mathematics, coordinate geometry in mathematics, these are topics which you just have to understand, and then there can't be difficult questions made in these topics. That's what I believe, right? So we'll just look at what happens in wave motion, right? We'll try to understand. So I'll first write the equation that you guys are familiar with. Y is equals to f of x comma t. This is how a wave motion is represented. How is this representing wave motion? That is the question. You guys know this is coming from mathematics, where y, which is a function, y is something which is a function of x and t. That means I give x as an input, t as an input, and I get y as an output, right? So I'm giving some x's and some t's as my inputs, and I'm getting some y's as my outputs. How is this leading to some wave motion, right? That is what the question is. So I'll actually do one thing. I'll also write the wave equation, which you guys already know. Y is equals to a sine kx minus omega t. So you would have been told that, okay, you can write this as y is equal to a sine kx minus omega t, or kx plus omega t, or cos kx minus omega t, or cos kx plus omega t. All of these are valid wave motion equations, right? This is something which is a standard. This is the equation of a sinusoidal wave, right? And this wave is definitely moving, provided your k is not 0, right? Provided your omega is not 0. So let's see what's actually happening. This is what your sinusoidal wave looks like. And I say that this wave is moving when I look at this equation. How can I say this, right? So before this, what you have to understand is, any equations which represents wave motion has to satisfy this condition. Dou square y by dou t square is equals to k into dou square y by dou x square, where k is your velocity square. These equations definitely look crazy to you right now, but it's very, very simple, because all you have to do is you have to look at the wave equation, and that is your y. So first you'll have to differentiate this twice with respect to t, keeping your x as constant. That is why this dou symbol is coming. This dou symbol means that I'm keeping x as my constant, and x as a constant I'm differentiating only with respect to t. And that should be equal to some constant k into, when you take t as a constant and differentiate only with respect to x, twice you'll get dou square y by dou x square. So this term should relate to this term by a constant. This constant is the velocity of your wave motion. If this happens, condition number 1, and at no y, or at no x and t, y becomes undefined. If these two conditions are ensured, then I will say y represents wave motion. So condition number 1, this has to be obeyed. Condition number 2 is that your x and t, if I give any input of x or any input of y, anything I can give. I can also give infinity, but my y shouldn't become infinity. If my y becomes infinity, then this cannot represent wave motion, right? So now I've told you, okay, that you've got an equation, y is equals to something. You have to differentiate that twice with respect to t, then twice with respect to x, keeping t as constant, and then they should relate by some constant k, and that k is your v square. This has to be obeyed, and then the second condition that at no x and t y becomes undefined. Undefined means infinity, obviously. At no x and t this should happen. If these two are ensured, this is your wave motion. That equation would represent your wave motion, right? So this is done. Okay. Now let's look at why and how is this motion happening. So is it actually that the wave is moving, right? It looks, so there's something that I would like you to remember here. If you have y is equals to sine kx minus omega t, if you have a minus, then your wave moves from left to right. You have to remember this, right? You can obviously derive this, but then in the exam you won't have the time to, right? And you might get direct questions on this. If you have something like y is equals to kx plus omega t, then your wave is moving from right to left. If minus, then left to right. If plus, then right to left. Okay. This is how this plus or minus defines the direction of velocity, right? But is the wave actually moving? What is actually happening? Let's look at that. So this equation that you see here represents the equation of a transverse wave. Why am I calling it a transverse wave? Because you have x and you have y, and y is perpendicular to x, right? Y is perpendicular to x. That is our standard convention. Let's look at what happens in this equation. Okay, so what happens is there are particles in the medium. Okay, air particles or whatever the medium is. Such like you have particles. Let's look at air, for example. What's happening is these particles are oscillating along the y direction. So right now this particle is having this much velocity, and its position is somewhere here maybe. So this particle that you see here is somewhere here. This particle that you see here is somewhere here. This particle that you see here is somewhere here. This particle is somewhere here, and then it keeps coming down, right? So this particle is here, and this one is here. So that's how it takes this shape. All right. That's how like these particles might be down. Okay. So that's how it takes this shape. This is what is a sinusoidal wave. So what is actually happening is this y that you see here is the position of this x. What is x here? This is x equal to 0, maybe x equal to 1, x equal to 2. So x is, I would say, the roll number of the particle. So if I fix an x, I fix a particle. Because if I take this as my x equal to 0 and this particle has some x equal to x1 distance, then if I put x1 in this, that means I'm talking about that particle whose x coordinate is x1. So that means I went to that particle putting x equal to x1. Okay. And now what's happening is all of these particles are just oscillating along the y-axis. So that's why y is the position of that particle x. Y is the position of the particle x at time t. So now there's one more factor coming, time t. That means this position of each x is changing with time. So like after some instance, your wave might look like this, right? So it might happen that this particle which was here went higher up, okay, and this particle which was here went further high. This was here, went further high, and this came slightly low, and so and goes on, right? So now your wave looks like this. So now this particle was here, now it's here, right? So what happens is, if you closely look at this, so I have not drawn the proper diagram here for you to understand better. Or you could also, or in fact, these are very close cases. Let me take an even more extreme case so that you visualize better what is happening. Take it for instance that after some time, this particle that you see here, it comes down. Okay, so this particle that you see here, it comes down. So it's here now. This one is somewhere here. This one is somewhere here. So your wave is now like this. So what's happening is, there was this part, this bottom part and this top part. Now you have the bottom part here and the same top part here. That means if you look at this, the wave has shifted. It looks like the wave has shifted, but what is happening is, the wave takes that shape because the particles now have changed their positions with respect to y-axis, right? So that is why it feels as if the wave is moving, but actually the waves are not moving. It is just that the particles are oscillating along the y-axis, and if I keep taking a picture of their motion, right? So if I keep clicking the motion, it will feel as if the wave is slightly moving ahead, right? That is what actually happens. So what are the parameters that will define the wave? I need to be sure about the y position of each x particle at a time t. Because what's happening here? There is a fixed y coordinate. At this y coordinate, different at this y, so like let this be y equal to 1. At y equal to 1, different particles are coming at different instances of time, right? So for example, this first particle might be here at time t equal to 0, and maybe the, what do you say, seventh particle here might be here at time t equal to 2 seconds, right? So at t equal to 0 this was the case, at t equal to 2 this is the case. So that means y is a function of both x and t. If I fix an x, that means I'm talking, if I fix x, I am talking about the motion. So if I fix x and don't fix t, I also have to mention that, and don't fix t, I'm talking about the motion. I'm talking about the motion of a fixed particle at all times, right? So this is what it is. If I fix x, that means I went to the particle, and if I keep changing t, I'll be able to see, okay, how is that particle at different instances of time? Where is the particle? What is its y? If I fix x, if I fix t, then what will happen is, if I fix t and don't fix x, then for each x I'll get a separate y. That means at a specific time, where is every x is what fixing t and not fixing x will give me. And if I fix both x and t, then I'll be able to see where is a particular particle at that instant of time, the fixed instance of time, right? I hope you understood. The two variables are controlling this y, where x is your roll number of the particle, t is the time, right? Now there are two velocities. So let me make some more space, make it slightly clearer for you.